Namaste, welcome to our course on linear algebra through geometry. In this lecture, we look at operations on matrices. The easiest one is addition. Let us see what is addition. These operations may sound very simple and elementary, but mathematics requires everything to be stated, and therefore, we treat them here elaborately. Suppose A and B are two m by n matrices, then C, which is sum, is equal to A plus B, is that m by n matrix whose ij elements is the sum given by Cij is equal to Aij plus Bij. Two matrices can be added only if they are of the same size. Now look at the example. Here A and B are added, corresponding elements are added. So finally the sum C will be 2, 1, 4, 5, 6, 5, 3, 8 corresponding to A and B matrices. Let A be m by n matrix and K be the arbitrary scalar. Now we have to do some scalar multiplication to the matrix. Let us see that. Then C is equal to K A is the matrix that is obtained by the multiplication of a scalar K with A and whose ij element is given as Cij is equal to K Aij, is the product of K with Ij. So take an example. A is equal to 1, 2, 3, 4, 4, 2, minus 1, 3, let K be 5. So when you multiply that scalar factor with the matrix A, it will be 5, 10, 15, 20, 20, 10, minus 5, 15. If K is 0, then Ka will be also be 0, the 0 matrix of the size of A. If A and B are of the same size, then A minus B is equal to A plus minus 1 into B. Here the scalar factor is minus 1 for the B matrix. Let us look at properties of matrix operations. These operations we will also see when we do operations on vectors in the later modules. Let A, B and C be m by n matrices and let K1 and K2 be scalars. Then the following properties hold. Commutativity: A plus B is equal to B plus A. Add A with B or B with A, the result is same. Associativity: A plus B plus C in brackets will be A plus B in brackets plus C. Existence of additive identity element: the sum of any matrix with 0 matrix is the matrix itself. A plus 0 m by n is equal to A. Existence of additive inverse element: A plus minus A is equal to minus A plus A. Therefore the answer is 0 matrix of m by n. Similarly, A plus minus 1 into A is 0 m by n. Distributivity: K1 into A plus B in brackets is equal to K1 into A plus K1 into B. Scalar multiplication distributes over matrix addition, that means scalar gets multiplied with all the other matrix. Multiplication distributes over addition. So suppose K1 plus K2 is multiplied with matrix A, then it will be K1 into A plus K2 into A. Associativity of scalar multiplication is K1 K2 into A is equal to K1 into K2 A. Identity property of scalar multiplication, 1 into A is A. Note that we have defined scalar multiplication and not multiplication of two matrices. Now, let us go to transposing of a matrix. Given a matrix A of size m by n of real number entries, we define the transpose of the matrix A as that n by m matrix whose ij entry is ji entry of A. Now, look at the example. A is equal to 1 2 3 4 4 2 minus 1 3, then A transpose is equal to 1 4 2 2 3 minus 1 4 3. Here the row vector of A is the column vector of A transpose. Transpose of the matrix is denoted as A superscript T. A square matrix A is said to be symmetric if A transpose is equal to A. We can see that in the example A is equal to 2 1 1 2 is a symmetric matrix. Symmetric matrices play important role in many applications and have many interesting properties which will be covered in the later lectures. A square matrix A is said to be skew symmetric if A transpose is equal to minus A. Suppose A is equal to 2 1 minus 1 2, then A transpose is equal to 2 minus 1 1 2. However, we see that when we are transpose, the following happens. The diagonal elements reflect themselves. The elements above the main diagonal of A reflect into the elements below the main diagonal of the matrix A transpose. This means for a skew matrix AII is equal to minus AII, which means the diagonal elements of skew matrix must be 0. Example, A is equal to 0 2 minus 2 0 is a skew symmetric matrix. Similarly, you take 3 by 3 matrix, A is equal to 1 2 3 minus 2 4 5 minus 3 minus 5 7 is not a skew matrix because the diagonal elements are not 0, despite of the off diagonal elements being negative of those of A. Let us look at the properties of transpose operation. For any two matrices of the same size A and B, let us see the properties. 1. Transpose of sum of matrices is equal to the sum of transpose of the matrices. For example, A plus or minus B transpose is equal to A transpose plus or minus B transpose. Transpose of matrix transpose is the matrix itself. That means A transpose over of a transpose is equal to A itself. The transpose of a scalar multiple of matrix is equal to the scalar multiple of the matrix transpose. K1A transpose of K1A is equal to K1 multiplied by A transpose. For a square matrix A plus A transpose is always symmetric. Similarly, for a square matrix A minus A transpose is always skew symmetric matrix. The proof is given below. Some numerical examples. Let us take a matrix 3 by 3, 1 2 3 4 5 6 7 8 9 and its transpose is 1 4 7 2 5 8 3 6 9. You see the row vectors become column vectors in the transpose. Suppose we add A with its transpose, A plus A transpose is equal to, we get 2 6 10 6 10 14 10, 14, 18. Now we will try to subtract A minus A transpose for the above example. A is 1, 2, 3, 4, 5, 6, 7, 8, 9 minus the transpose, if you subtract, that is 1, 4, 7, 2, 5, 8, 3, 6, 9 is equal to 0 minus 2 minus 4, 2, 0 minus 2, 4, 2, 0. So, here what you see, the diagonal elements are 0 and the off diagonal elements are reflect each other with a minus sign, that 2 and 2, minus 2, minus 2, minus 4, minus 4 we have seen. So, this is a skew symmetric matrix. So, if you subtract from A its transpose, you get a skew symmetric matrix. Given matrix A, we define the trace of A as the sum of diagonal elements of A. Trace A is sigma n I to 1 is equal to aii. We denote the matrix trace as TRA or trace A. For example, in the above example 1, 2, 3, 4, 5, 6, 7, 8, 9, the trace A is 1 plus 5 plus 9, that is equal to 15. That means the diagonal elements are added. Now let us look at properties of trace of a matrix. For any two square matrices of the same size A, B, trace A plus B is equal to trace A plus trace B. Similarly, trace of A transpose is equal to trace of A. Trace K1A is equal to K1 trace of A is for some scalar K1. We will see later that trace of matrix is equal to sum of the eigenvalues of A. The matrix operations like A plus or minus B, Ka, etc. were straightforward. They were mostly element wise operations. What we mean is that if we define C is equal to A plus or minus B, then the ijth element of C is defined as Cij is equal to Aij plus or minus Bij. However, matrix multiplication operation is not straightforward. It is not done as the usual element wise operation. It is done slightly differently. Let us see how it is done. Let A and B are two matrices. Say A is an m by n matrix. Then for us to find the product matrix C is equal to AB, the B matrix must be an n by p matrix. C then has m rows and p columns. For A m by n, B n by p, finally C will become AB is an m by p matrix. Thus, the product AB is defined only if the number of rows of B is equal to number of columns of A. Let us see how matrix multiplication is done. Let A be 2 by 3 matrix A11, A12, A13, A21, A22, A23. Let B be 3 by 2 matrix. B is equal to B11, B12, B21, B22, B31, B32. We see that number of columns of A is 3 and the number of rows of B is 3. Thus, the multiplication AB is defined. However, we note that the product BA is not defined as the matrix dimensions do not match. We take the same matrices A and B as A11, A12, A13, A21, A22, A23, B, B11, B12, B21, B22, B31, B32. The product of A, B, C is equal to, there are three terms, A11 into B11 plus A12 into B21 plus A13 into B31. The second term, A11 into B12 plus A12 into B22 plus A13 into B32. Similarly, A21 into B11 plus A22 into B21 plus A23 into B31. Last term, A21 into B12 plus A22 into B22 plus A23 into B32. For example, C11, sum of products of first row elements of A with the first column elements of B. We can generalize as Cij is equal to Aik into Bkj, k being 1 to 3. The C12 is obtained as A11 into B12 plus A12 into B22 plus A13 into B32. C12 is equal to sum of products of elements of first row of A with that of second column of column elements of B. In general, A is an M by N matrix and B is an N by P matrix. Then the product matrix is A B is equal to is a M by P matrix. Cij is equal to AI1 into B1j plus AI2 into B2j plus AIN into BNJ is equal to is summation of Aik into Bkj, k being 1 to n. We again see that the product AB is defined, but the product BA is not defined as the matrix dimensions do not match. Let ABC be matrices for which the following operations are defined and K be a scalar. Then we have the associative law of multiplications says that A into BC is equal to AB into C. The distributive law of matrix multiplication says that A into B plus C is equal to A into B plus A into C. A plus B into C is equal to AC plus BC. That is, matrix multiplication distributes over matrix addition. The associative law of scalar and matrix multiplication say that K into AB is equal to Ka into B or A into Kb. That is, the scalar multiplication of matrix product is the same as the product of scalar multiple of one of the matrices and the other matrix taken in the same order. It is interesting to see that commutativity property of matrix multiplication may not hold always. AB need not be equal to BA. It is also interesting to note that if AB is equal to AC and A is not equal to 0 m by n, then B need not be equal to C. This is not the case with the product of two real numbers. If x, y and z are three real numbers and if xy is equal to yz, then y is equal to z. Example, A is 2163, B minus 1052, C is equal to 31 minus 30. AB becomes 3296, AC becomes again 3, 2, 9, 6. Let A, B, C be matrices for which the following operations are defined. Similarly, if A into B is equal to B into C, then A need not be equal to C. We know that if the product of two real numbers is 0, either one of them or both must be 0. However, this is not the case with matrix product. If AB is equal to 0 matrix M by N, then it is not necessary for A or B to be the 0 matrix. Example, A is 0 1 0 0, B 1 0 0 0, then A into B is equal to 0 0 0. Let us take the transpose. Transpose of product AB is equal to transpose of B multiplied by transpose of A. If A is a square matrix, then A to the power of 0 is equal to I, A to the power of 1 is equal to A squared is equal to A into A to the power of R is equal to A to the power of R minus 1 into A. In the case of real numbers, we know that xy whole squared is equal to x squared y squared. However, again in matrices this is not true. In general, AB whole squared is equal to AB into AB, but it is not equal to A squared into B squared, as A squared into B squared is equal to A into B is not equal to A into B into A into B. The order in which we do the matrix multiplication matters. Having looked at the various operations on matrices, we are now ready to look at solving the system of linear equations. Firstly, we look at the homogeneous system of equations. A system of linear equations with right hand side is equal to 0 is called homogeneous system of equations. A11 x1 plus A12 x2 A1n xn is equal to 0 on the right hand side. Similarly, A21 into x1 plus A22 into x2 plus A2n into x1 is equal to 0. Last, AM1 x1 plus AM2 x2 plus AMN x1 xn is equal to 0. In the matrix form, this is represented as Ax is equal to 0. We immediately observe that if all the unknowns xi's are 0, then the RHS of the linear equations will be 0. The solution where all xi's are 0 is called trivial solution. Thus, we see that the homogeneous system of equations is always consistent. It always has solution. However, the solution can be different. If you have a non-zero solution, we call it as the non-trivial solution to the homogeneous system of equations. A quick example reveals that whenever a homogeneous system of equations has a unique solution, it refers to the trivial solutions only. Now see these two equations. 2x1 plus x2 is equal to 0, x1 plus 2x2 is equal to 0. If you plot, it is the two lines are intersecting at origin 0. We know that our basic understanding of the geometry of two lines, if two lines intersect, they intersect either at unique point or they intersect everywhere. In case of homogeneous system of linear equations in two variables, the two lines already intersect at the origin, since the trivial solution always exists. If they intersect at any other point, they will intersect at every other point, that is, there is non-trivial solution that exists. Thus, a homogeneous system of linear equations either has trivial solution that is unique solution, or infinitely many solutions. Since homogeneous system of equations is always consistent, the no solution case does not exist. It is important to study homogeneous system of linear equations and its solution, as it reveals lot of information about the matrix rank, invertibility, if the coefficient matrix is a square matrix, etc. To summarize, in this entire module we looked at the idea of representing system of equations through matrices, some elementary applications of matrices in graphs, solving for currents in electric circuits, curve fitting, data science, etc. Geometric perspective of system of equations in 2 and 3 variables, consistent and inconsistent system of equations, some matrix definitions, matrix operations including addition, scalar multiplication and matrix multiplication, transposing a matrix and properties of transpose, homogeneous system of equations. In this next module we look at solving system of linear equations, matrix inverses, determinant of matrix, rank of a matrix. Thank you. Namaste.